So good morning. It's my great pleasure today to have Wenju Chai, Chief Scientist at the CSIRO in Australia, who has done incredible leading work on understanding El Niño in the context of a warming climate. And as you know, we've had some papers to read on this topic, and today we have the privilege of having Wenju Chai to talk to us directly through a lecture on Zoom. So Wenju, without further notice, thank you so much. And I will turn off my video to reduce your bandwidth load. And so welcome.
Thank you, Manuel. And it is also delightful for me to talk to your student. And as I say, we collaborate a bit and also with Kim. And so I'm quite sort of feeling relaxed to be able to talk to your student directly and also to communicate with you, to learn together in this 1 hour. And so I'm going to talk about how El Nino and La Nina may respond to global warming. So we should start with the mean circulation in the equatorial Pacific. So the mean circulation in the equatorial Pacific features trade wind, easterly wind, that blows from the east to west, piling up warm water over the western Pacific. And the warm water in turn supports a very strong deep convection in the western Pacific, the biggest rain area on Earth. And so that these rising motion goes too high in the atmosphere, and there is a return flow back to the surface of the eastern equatorial Pacific. And so we call it as water circulation, right? Now this trade wind also drives a strong sort of slope towards the east of the thermocline, and that with upwelling of the ocean, so that allows the cold water to be able to arrive at the surface, in turn reinforcing this zonal gradient, in turn reinforcing the wind and that system, water circulation, and the interaction between the ocean thermocline and temperature gradient, what we call balcony feedback. I'm sure you all know this. So this is on a seasonal sort of time scales. The wind would change with the sun, strongest in June, May, but weakest in the southern summer and so on. So these seasonal sort of this seasonal circulation is interrupted every 2 to 6 years when the trade wind relaxes and the warm pole shift towards the east. And so the zonal temperature gradient weakens, and we have the westerly wind anomaly, which suppresses the upwelling and deepens the thermocline. And when that happens, it actually promotes the warming in the east. So this is the balcony feedback on the internal time scale. So when the warm pool shifts to the west, taking with it is the deep convection. And so this is a reorganization of the circulation. You've got anomalies. Along the western Pacific, you've got drought because the rain bands moves away, particularly in Australia, in Java, Indonesia. But in the Americas, California or Chile, we have more rain than normal, and so on. But the important thing is this is also a positive feedback between the westerly wind, the deepened thermocline, the weakened gradient, and the shift of the convection towards the east. And the La Nina is the opposite. So we have the trade wind becomes more intensified and more concentrated, and the mean circulation shift a little bit, but more intensified. And so stronger upwelling, reinforcing the cooling, extending to the central Pacific. In fact, the anomaly center is in La Nina is more likely to be at the central equatorial Pacific. And we know there are strong impacts when this happened during El Niños. For example, the 1997, 1998, the strongest El Nino events. So we call 1997, 1998 because it's December, January of the December of the 1997, January, February of the 1998. And when the upwelling was shut off, you had the marine life die en masse because the food they prey on, the anchovy, disappeared. Normally that come with upwelling high nutrient water. And of course we have flood in Peru and so on during that strongest events of the 20th century, in fact, so far. And in Australia, with the Western Pacific countries, we had a flood in 283. It's also the second strongest El Nino. So we have dust storm, we have bushfire in Australia that killed many. In 1983, what we call Ash Wednesday, because it's a January, February period when the drought occurs. And in the South Pacific, we have, in the climatological sense, we have the intertropical convergence zone or South Pacific convergence zone. So during El Nino, when the warming extends towards the east, the surface warming area become bigger along the equatorial region, the South Pacific convergence zone shift towards the equator, and the ITCZ also shift towards the equator. And that, for example, the South Pacific convergence zone, or SPZZ, which provides rain for the island country. So when it shifts away, it causes drought. Where it shifted to, it causes flood and food and extreme events. The feature of the shift, it causing extreme event to the vulnerable island countries. During La Nina, of course, the SVCZ move away from the equator, just a bit of opposite to the El Nino. And 1997, 1998, extreme El Nino was followed by the biggest La Nina we have ever seen since 1900s, since observation starts. And in 1998, that La Nina was really humongous. In China alone, it kills tens of thousands, and it displaced more than 200 million people. And so that occurs, that was really big, really massive. And in Australia, we have floods in Brisbane, Eastern Australia, Northeastern Australia, and the last La Nina, well, not the last La Nina, but another sort of La Nina followed the 2015-26 strong El Nino. In China, we also again had that kind of huge flood. Now, ENSO, El Nino and La Nina together really affects many walks of life, of area as well. For example, the Indian Ocean dipole affects monsoon. During El Nino, we tend to have weaker monsoon. And it also affects the shorter time scales, tropical cyclones. For example, 1998, the Atlantic saw the most vicious tropical cyclone season. And of course, it affects Indonesian true flow. El Nino also affects tropical North Atlantic, and so causing drought in the Amazon area, and so on. Just to convey the message, it's actually most consequential climate modes of variability. Now, we describe El Nino in terms of ocean temperature, or in terms of what we call the Southern Oscillation Index, the sea level pressure between Tahiti and Darwin in Australia. But oceanographers tend to use the Oceanic Index, and this is the blue area is what we call Niño 3 area. Often we use the sea surface temperature anomaly to describe the Eastern Pacific El Nino. And there is another region that I often use is Niño 4 in green. Niño, this is Central Pacific El Nino. So as you will know, you'll see that I'll talk about there are different kind of El Nino, Central Pacific El Nino and Eastern Pacific El Nino. But we also can use a combined index referred to as Niño 3.4. It's combined of the two. And so that's we often use. And much throughout this talk, I'm going to use the oceanic index in a lot of paper that we discussed. The issue really, because of the strong impact, the issue is how ENSO will respond to greenhouse warming. And that is a question that has been challenging scientists for many years. And I'll give you a bit of history. In 2010, we were invited to write a review paper. And in that paper in 2010, we took advantage of all the available models in the world that run through the historical period with observed carbon dioxide, ozone, and the aerosol, as well as volcanic forcing into the future, projected emission of carbon dioxide and methane and ozone as well. And you can see here we are looking at the standard deviation, which standard deviation reflects the variability of Niño 3, the Eastern Equatorial Pacific SST, sea surface temperature. And you can see half the model, this is a difference between 20th and 21st century. Half the model produce an increase and half the model produce a reduction. And so there is no intermodal consensus in terms of how El Niño's sea surface temperature variability may change. And by 2015, we were asked again to write an update of review paper. I think many include in the reading of this paper. And so, again, at that time, we had the CIMIT-5 models, coupled model intercomparison project that was participated by a lot of model groups. And the combination of the two is fed into supporting the IPCC report. So what we call IPCC's assessment report 5 in 2013. So in this picture, they show the pre-industrial condition of the Niño 3 standard deviation and variability and 20th century RCP 4.5 medium emission and high emissions. And there is a huge range across models, and one of them is the median, the other one is the average. Again, you can see there is no sort of discernible change because the range is so big, and they're all encompassing on natural variability. Pre-industrial, for example, this without climate change, the range are quite similar. So there is, again, no consensus as to how ENSO's sea surface temperature variability may change. However, at the time, many models, majority model, produce a strong consensus on the mean circulation change in the Pacific. And I'm going to talk a little bit of these circulation changes in the mean. Weakening water circulation with faster warming in the Eastern Equatorial Pacific. So weakening water circulation, like during El Nino, there's a weakening of water circulation because there's a warming here. And so weakening water circulation means that the wind that's blowing from east to west will be weakened in the mean climate. The upwelling will be weakened. The oceanic currents, which normally flow, upper oceanic current flow from east to west, will be weakened. And there is also a strong intermodal consensus of the thermocline shallowing. So this black color is the present day climate, 20th century, for example, in this picture. And the red color is the 21st century. So there is a shallowing in the thermocline, and the biggest shallowing is in the central western Pacific, eastern Pacific, little shallowing. Yeah? And the upper ocean is warming faster. warming faster because those heat goes through the upper ocean first, and before it can diffuse down, it's staying there for a while. So the stratification increases. Maritime continent, because half its land is warming faster than the oceans of it. And if you average across equatorial Pacific, then the off equatorial Pacific is warming faster. It turns out that each of these features or in combination, some of them in combination, could have a strong implications for ENSO variability change, at least some of the characteristics. For example, the SST variability may not change, but rainfall variability could change because when the mean changes, it's easier to shift convection along. So when El Nino occurs, convection shift from Western Pacific to the Eastern Equatorial Pacific. Convection always follows where the maximum temperature is. If the mean is warming faster already, it's easier to generate extreme, even with the same warm anomaly, for example, during El Nino. And so our first implication for that was a paper that we published in 2012. We said, well, because average across Equatorial Pacific, Equatoria is warming faster than the off Equatoria. So it's easier for this convergence zone to shift towards the equator. So those extremes shift towards equator such that the SPCZ become zonal or east-west oriented. Those kind of extreme events will increase. In fact, will double, simply because in the future climate, Equatoria is warming faster than the off Equatorial Pacific region. And then from there, we also look at extreme El Nino. Here we define extreme El Nino in terms of rainfall, convection adjustment, convection reorganization. So here we are looking at extreme El Nino of 1982-83 and 1997-98, two extreme El Nino events, the strongest of the 20th century. And we are doing the composite to try to distill the feature, the characteristics. So we are looking at December, January, February rainfall and sea surface temperature. You can see during those events, the warm pool extend across. The boundary is actually this purple color. The warm pool extend across from the Western Pacific, defined as the boundary is 28-degree isotherm. And the green is the rainfall mean value, average value during those two El Ninos. Rainfall in terms of 5 millimeters per day over the whole season, December, January, and February. You can see the whole rainfall also extend across. And because we normally have very cold in the east, it's very dry and quiet. Now rainfall is humongous, it's very big. And why? Because of the temperature anomalies. The warming structure is very interesting. So if you take two boxes of temperature of equatorial box difference from the equatorial box. So meridional box 1, right, minus equatorial box is less than 0. It means that during those events, right on the eastern equatorial Pacific is actually warmer than the north of the equatorial region where the ITCZ climatologically sits. ITCZ is located there, intertropical convergence zone. So the convergence zone actually moves south, and that generates that big reorganization. Not only the convection here shift towards the east, the ITCZ also shift towards the east. And you can see from this schematic, during extreme El Nino, not only the Western Pacific shift to the east, the ITCZ also shift to the east. And that lead to that massive reorganization, huge flood in Ecuador, in America, Chile, and in Peru. And so here is the meridional gradient, which we're going to use quite a bit. So that gradient, north equatorial minus equatorial region becomes negative in these two events. This is 2015-16. And this is the rainfall in the eastern equatorial Pacific region averaged over December, January, and February. And you can see it's nonlinear relationship. It's a huge increase. Normally, it's very calm, very quiet. Rainfall is very small. Yeah, only about 1 millimeter per day average over the whole season, but it could go to 10 times. And so you calculate rainfall skewness. The rainfall skewness is very big because it can grow so big, positive. Now, we can define extreme El Nino in terms of rainfall as when the DJF rainfall average is greater than 5 millimeter per day, every day, on average, as extreme El Nino events. And you use that definition, you're going to look at climate models. And at the time that paper was done, we had 20 models. And so here, 5 millimeter per day, DJF averaged. This is a 20 model, each had 100 years. So we have 2,000 years of virtual climate. And there are 110, that means 1 in 20 years, one extreme event in 20 years. But in the future climate, at the time we call it future climate, this second 100 years, the same number of years, the extremes doubles. So it increases from 1 in 20 years to 1 in 10 years. And the intermodal consensus is really strong. 17 out of the 20 models. So that's not random. And something is working. Otherwise, you wouldn't get that high intermodal consensus. And so that is the paper. I think it's also included in Menu's recommendation of readings. So basically, in the present day climate, to ship convection, to have this massive reorganization of the convection, you need 2 units of anomalies, 2 contours here. But in the future, because it's already warming faster, you don't need 2 units of anomalies. You only need less than 2 units. So even if SST variability does not change, the extreme rainfall, El Nino extreme rainfall, or we call somebody call them extreme convective El Nino, doubles in frequency. And so Paris Agreement was announced, and the question is, does it provide any sort of relief? I think it will, but is there any big sort of delay effect? So in that paper, we look at 5 models that runs to 2300s, and here we are looking at the RCP 2.6. That was the emission scenario that could take us to the Paris Agreement target of keeping the global warming below 2 degrees relative to industrial levels. Yeah, and so the black color is the global mean temperature. You can see like 2050s. Yeah, temperature stabilized. This is the meridional gradient reversing sign times -1. The gradient, though, yeah, this is the frequency in 5 models and the range, and the orange color is the average of the 5 models. The meridional gradient continued to weaken, -1, for another century. And similar picture here, we are actually calculating every 31 years, we calculate 1 value so we can move the window forward, see the evolution. And this is the frequency. The black color is the same, global mean temperature. The frequency continued to increase for another century, even if we could achieve the Paris Agreement by 2050. So at the by now we are still very much focused on rainfall. So the conclusion there was that under global warming, rainfall sensitivity to sea surface temperature anomalies increases, even if sea surface temperature variability does not change. So the extreme drought and flood will increase. It's projected, it's likely to increase under global warming, even if we don't know how sea surface temperature may change, or even if sea surface temperature variability may not increase. And the next phase is we go into a struggle of how to look at the sea surface temperature variability, how it may change. Here, we are looking at the weakening water circulations, the consequence of weakening water circulation. As I mentioned, weakening water circulation means that trade wind reduces. The oceanic currents, which in the surface also flows from the east to west. Those currents would weaken. Now, one of the biggest puzzle in El Nino is that some of the El Nino, the 82, 83, 1997, actually propagate from west to east. We know the mean current actually flow from east to west, but most of the El Nino, most other El Nino actually follow the mean direction from east to west. Those two extremes, for example, the anomaly propagate from west to east. So we call eastward propagating strong El Nino. And that's pretty odd. But when we look at when the reanalysis become available, we look at the anomaly, the oceanic current, zonal current, upper oceanic zonal current anomalies. The total current, in the upper 50 meters, average across equatorial Pacific. We find that these strong events, 82, 83, 97, 98, in a short period of time, actually during the development to mature season, the oceanic current actually reverses. And we thought that is what accounts for this fundamentally. And then the question comes, how those events may increase. And this is one way to tackle how extreme El Nino may change. So you would see, because the weakening upper oceanic currents, even if oceanic current variability does not change, we should be able to see more eastward propagating El Nino events. And sure enough, we look at all these 34 models in that study. This is a study by my colleagues, and we put all of them together in terms of Niño 3 indexes. In order to put every model together, we normalize first. Those are technical issues. And surely enough, we see in the future, the eastward propagating events increases quite a lot in terms of the red color in the future, and in the present day in blue. But many of the increases correspond to when the Niño 3 index is actually small. And so if you then separate out into intermodal, there's not a lot of intermodal consensus in terms of eastward El Nino / extreme El Nino. Because in the future, some of those eastward propagating El Nino may not be extreme, although in the present day climate, they are extreme. And so this issue of how ENSO sea surface temperature variability may change is still an open question by the time this study was conducted. Now, the other beam climate change, like the shallowing thermocline and faster warming in the maritime continent. Now, I tell you about when the extreme El Nino occurs. The cooling, the center of the cooling is more to the central Pacific. And the characteristics of extreme La Nina is that the deep convection is concentrated in the maritime region. Now, warming in the maritime continent will promote convection to move to the region, to the maritime continent. And the cooling, the shallowing in the thermocline will promote cooling. So our inference is that extreme La Nina events should also increase under this kind of mean state change. And that we have this following up paper in NCC in 2015. Again, we go and look at definition of extreme La Nina. So here, if we have a Niño 4 sea surface temperature index, and we have zonal temperature gradient between maritime continent and Central Pacific, where the La Nina center is, we find that there is a beautiful relationship. And the two most extreme events in the 20th century, 1988 and 1998, was in the upper left corner, and they are greater than 1.75 standard deviation. So we thought if we use this relationship, properly detrain the temperature in all the models, we can look at whether extreme La Nina event may change or not. And surely enough, at the time, we had 21 models, Niño 4 index, zonal temperature gradient, and these are the strong extreme La Nina in the present day climate, 100 years. I think by the time this study was done was 1900 to 1999, this period, and this is 2000 to 2099, so 20 years and 21st century. And so these extreme La Nina in 2100 years of virtual climate, the frequency increased by around 70 to 80%. And the bracket is the extreme La Nina that occurred after an extreme El Nino, as we've seen in 1998, 1997, and 1998, 1999, and La Nina. So a lot of increase occurs. A lot of increase in extreme La Nina occurs in a year after an extreme El Nino in a future climate. Now the weak La Nina events tend to decrease. Even in a more moderate weak La Nina, you can have this definition. Yeah, and I think it's quite reasonable because the mean state has changed, and you also have an extreme El Nino increase. What happened to the extreme El Nino is during extreme El Nino, the westerly wind normally takes the heat out of equatorial Pacific and released to the atmosphere or stored in the off-equatorial region. So this is the thermocline depth difference between the two strong events and the all events average. You can see there's a shallowing of thermocline maximum in this region, which is very conducive to cold water coming from subsurface to the surface. Normally, the thermocline in the Central Pacific is very deep, and the cold water wasn't able to influence the surface. But after an El Nino, it creates a condition. So a lot of La Nina tend to occur after an El Nino because of this effect, heat discharge during El Nino. So we just look at extreme events in this case. This study is the first time anyone used sea surface temperature to describe how ENSO may change. But again, it's only focusing on the extreme events. So we want to go back to the variability in terms of the sea surface temperature index. And so we have to overcome this lack of consensus. Why there's no consensus? The lack of consensus was again highlighted. This is a CIMET-5 model, a couple model intercomparison project 5, which supports AR5. Yeah. AR5, huh? AR5 means assessment report, IPCC assessment report 5. Yeah. So in the CIMMYT file, we have half really. 16 produce a reduced variability, but the other 18 produce a reduction, an increase. So no consensus, almost perfectly no consensus. This is in terms of Niño 3. But what does it mean by using Niño 3? What's the assumption? So when you stay out from the convention, when you're using Niño 3 for all models and for observation, you are assuming that all models produce an anomaly center in the Eastern Equatorial Pacific, as in the observations, right? Is that true? Is it appropriate to take Niño 3? And the answer is no, you shouldn't. And so that led to another paper that in 2018, Nature had a news and review saying that it's a milestone. Yeah, but let me tell you a little bit. So we know that El Nino has two types of El Nino, principally. One is in the Eastern Equatorial Pacific that tend to be very strong, and the other one is in the Central Pacific that tend to be weak. And so this is I'll talk about this E and C, but here you just need to know that there is two center of location where El Nino tend to occur, right? We call bimodality of El Nino. And in the east is stronger, right? And in the central is weaker. Of course, there are some events which is a mixture. 2015-16 El Nino is a mixture, very strong. Yeah. In terms of La Nina, although the center could be also in the east, but the center tend to be more likely in the Central Pacific. So this is a 1995 El Nino, La Nina, weak La Nina, and 1998 strong, the strongest La Nina. You can see they are quite in this. The maximum is in the Central Pacific. So we have El Nino, two type of El Nino, and their location is in Central and East. La Nina tend to be in the Central. So if you use one index, it's not appropriate. You need at least two indexes to describe the diversity of ENSO events, El Nino events, or as opposed to La Nina events as well. And one of the ways to do it is, this is in 2015 paper, is to identify the average pattern and another pattern that modify this average so that you can have the diversity. And this is done through what we call empirical orthogonal function analysis in the observation. And you get a time series for this pattern and a time series for this pattern. And it turns out this two pattern, the first principal component, the time series associated with this pattern, and the second principal component, PC2, has a nonlinear relationship. And the two extreme El Nino, 82, 83, 97, 98, and the two extreme La Nina are on both sides. This is 98, 98 La Nina or 88 La Nina. And so let's say extreme El Nino. Extreme El Nino is the difference between these two patterns. And so you take a difference, you get a maximum warming in the east, and that could be represented by Niño 3, almost approximately represented by Niño 3. And so we can have an Eastern Pacific El Nino index as what we call PC1, principal component 1, minus principal component 2, divided by square root so that they are standardized. And the La Nina is both negative, so these two patterns has the reverse sign, but the sum of both. So Central Pacific El Nino, the sum of the two give you this pattern. center in the Central Pacific because this offset, and then you get a maximum warming in the Central Pacific. La Nina just reversed the sign. So we can actually use these two indexes, C index and E index, to describe the diversity. And in doing this, this is all very objective. There is no human factor involved. It's all mathematical. These two patterns are orthogonal. The correlation, simultaneous correlation, is zero, but they nonetheless provided this nonlinear relationship, which actually reflects physical processes. I'll talk a little bit in what I will show below. And you can look at all the analysis data, and you again can get this in the DJF. You can get this beautiful nonlinear relationship in a quadratic relationship. This is PC2. We can write PC2 as a PC1's nonlinear function. It's alpha, and beta linear coefficient. Alpha is the nonlinear coefficient, and alpha for all the observation together is about minus 3.1, 0.31, minus 0.31. Now that is what we want to use as a way of diagnosing our model that we are using. So in the observation, I show you we have C index and E index through this. Now let's just have a look at the C index. C index really reflects a lot of weak El Niños. Positive is El Niño in blue, and strong La Nina, 1998. Yeah. E index is strong El Niño, 1997, 1982, 83, 1970 to 73. So you can see that E index, the positive can grow very big. C index, the negative can grow very big. So we call skewness of E index is positive. Skewness of E index is negative. Now, we need to remember the center of this positive skewness is actually the center of Eastern Pacific El Niño by definition. The center of negative skewness is actually the center of CP ENSO, again by definition. And the negative skewness is mostly due to those extreme La Nina. The positive skewness is mostly due to the strong El Niño. Yeah, that's basically, that's what the definition means. Yeah. So why we have this kind of bimodalities? So in the Central Pacific, convection readily occurs. When convection occurs, you have the westerly wind feed into the convection, so that the hot air rises. So when the warm occurs, hot air rises, wind increases, and when it cools, you get the wind reduces, and the westerly wind or easterly wind increases. But you can see that it's not linear. Here, the slope, the sensitivity of wind to sea surface temperature anomaly in the Central Pacific, they are not linear. So when convection occurs, the winds increases bigger. So the ratio between these two is 1.5 in the Central Pacific. In the Eastern Pacific, now it's normally very cold. You have to warm a lot for convection to be triggered. So it's, you don't, this is Portugal anomaly trigger convection, 0 here. Here you need to be quite large in order to trigger convection. But once convection is triggered, you are in the Eastern Equatorial Pacific, where the positive feedback between ocean temperature, upwelling, reduction in El Niño, and wind become much stronger. So the wind's response increases dramatically. And so it often occurs here, but in some years when it occurs in the Eastern Equatorial Pacific, this slope is much stronger than this slope, a factor of 3, right? And so that's why you have these two regimes, East and Central Pacific El Niño regime. Of course, there are some events which occur in between. So convection response in the model able to a model is able to simulate that is fundamentally important. And we can apply this EOF analysis as we do to the observation to all models in the world. Causality, they train the temperature anomaly. They train them because there's some trend, right? 34 models. And we can get this E-index pattern, Eastern Pacific El Nino pattern, because we had an index. We can just regress onto it, right? In one model, this is the Eastern Pacific El Nino pattern. In this model, CSM. In another model, is this pattern. Now, these two patterns are very different in the position, in the center of the anomaly. They are both Eastern Pacific El Nino. They are not, it is not appropriate to represent them by Niño 3. If you use Niño 3, you don't know what you don't know what you are getting, right? But if you represent the Enso variability in terms of index, allowing each model's pattern to be different, then we can see how that index variability may change. But not all model is able to simulate the nonlinearity that I talk about. So even so, if we look at now all the models in the E-index, right? Now we have the model consensus is stronger now. So before we had half-half. This is half-half I talk about. But now we have 24 out of 34 models generating an increase in Eastern Pacific index, right? No selecting models, right? This is CIMIT 5, CIMIT 5. Early generation, then the generation that we have, CIMIT 6. But we need to choose model because models are notorious bad in simulating convection. They are not able to simulate the nonlinear processes associated with ENSO. So in the observation, we have these three values: alpha skewness, positive skewness of E-index, C-index. We can calculate for every model, every 34 climate model in the world. And this is the multi-product mean from observation. So this is E-index skewness. This is alpha. Greater skewness, positive skewness, E-index, greater the amplitude of the alpha. Alpha is negative. Beautiful relationship. 0.92. 0.92, yes. And C-index we know should be negative. The observation is negative. And again, the greater the alpha in amplitude, the greater the negative skewness in the amplitude of the C-index. So alpha really is a measure of the nonlinear processes in the models as reflected in those two skewness. But some models are really bad. They even simulate a negative skewness index or positive alpha. Positive skewness in C-index, which is just so wrong because it's to be negative, right? And we can use that alpha amplitude. Observation is, as I told you, 0.31. If we choose models with a threshold as half in amplitude, half the amplitude of the observed, we get 17 models. And those are the 17 models that give you this nonlinear relationship that we saw in the observation. And those are the bad models. And just to highlight that alpha is really a wonderful thing, linking diagnosable model parameters, objective parameters, and it linked to the processes of the nonlinear convective response to sea surface temperature anomalies. And this is some of the good models and some of the bad. And so these bad models, we are going to not use them. And I tell you, this is a good model. 17, sort of nonlinear relationship in the E index. This slope is much greater than that slope in terms of wind response to temperature anomaly. And this is in the C index. In the model, the slope differential is very, very weak. But this is, again, we are using only half of the observed nonlinearities. And once we select the models now, we look at the E index variability in the 20th century and 21st century. Two bars. Blue is the present day climate, 20th century. Red bar is in the future. Now, 15 out of the 17 models produced an increase in E index sea surface temperature variability. That's a very strong intermodal consensus, nearly 80%. And that translates to increased frequency of extreme El Nino now in terms of sea surface temperature variability. So DJF E index greater than 1.5 standard deviation is what we use to define an extreme El Nino. And the dynamics was also very interesting, very intriguing. So we know there's intensified stratification, warming faster in the upper ocean, and that would make the ASC coupling stronger because the same amount of wind is acting in a shallower thermocline. And so this increases the ocean atmospheric coupling. So we can look at define a gradient changes, average over the upper 75 meters, for example, take away the difference with 100 meters. And we look at the changes in the vertical gradient in those 17 models and the changes in E index variability scaled by global warming because each model has different climate sensitivity that make it warm a lot more, higher sensitivity get it warm, so we warm more, so we scaled it down by per degree of global warming. And you can see now there is a strong relationship, R squared, of 0.56. So correlation is around 0.75. Greater the intensification of stratification, the greater the increase in ASC coupling, leading to an increase in Eastern Pacific sea surface temperature variability. And we can also look at the C index. 11 out of 17 produce an increase in C index. Why? Because you have more El Nino lead to more extreme La Nina, and that then contributes to the Eastern Pacific, to the Central Pacific SST variability, and extreme La Nina events also increases in majority of models, and which is basically going back to the early study in 2015. Yeah. It now takes me to CIMMYT 6. I'm going to go to CIMMYT 6 quickly. CIMMYT 6, the simulation of convection is much better. In fact, when we look at around 30-something model, we use one-third in this paper, I think. I can't remember, one-third or half. We were able to select 23 models. And we look at the E index and C index. And you can see now in the Eastern Pacific El Nino, all the models produce an increased variability in E index in 23 models, right? And E index also increased in variability. This is the same deal, present day and future. But now using CIMMYT 6, where the convection parameterization has improved a lot. And we can do the same nonlinear plot for the present day and future. And you can identify extreme El Nino in orange, extreme La Nina in blue, extreme El Nino followed by an extreme La Nina in star. They all increases. So this is in the latest review paper. Just an update using CIMMYT 6. So CIMMYT 6 ENSO's change is actually much more the signal is stronger, it's much better. And now, in fact, both E index and C index have increased. There's no need to separate into E index and C index. You can just use Niño 3.4. You should get majority of models should produce an increased variability. Simply go back to the traditional index, because both C and E, Central and Eastern Pacific, SST variability of ENSO has increased. However, IPCC's latest report says that rainfall variability will increase, which is really quite old. And in the chapter 4, specifically on ENSO, it says it's virtually certain that will remain the dominant mode of variability, but there is no model consensus for a systematic change in intensity of ENSO SST variability over the 21st century in any of the scenarios. And what they do, they use 30 years to calculate the variability and moving forward for all models and show that there's huge range and marking around the ratio equals 1, future and present day variability ratio. But using 30 years is probably not appropriate, because in 30 years, internal variability is very strong, and climate change signal is not strong. Probably only 2-3 cycles of ENSO, 30 years, or maybe 4 or 5, but not enough. So if we use 100 years, simply 21st and 20th century in Niño 3.4, in SSP 585, this is the highest emission scenario in all IPCC, or high emission scenario. 43 models, right? 38 produce an increased variability. RCP 126, the one that could take us to the target of the Paris Agreement, 34 out of 39, again in the 3.4. So you don't need to separate E or C index. And other scenario, this two we talk about. So here we are plotting 20th against 21st century in a diagonal line. So majority of model is on this side of the diagonal line, which we talk about. 38 out of 43 produce an increased variability. Now, 126, 370, another scenario, or 245, medium scenario, again shows an increase. Now, you can also do other indexes. Niño 3, majority of models show an increase. So I think IPCC is being very conservative. Now, just 2-3 slides of outstanding issues. 20th century ENSO, there is, you believe in the data, there is an increase. So this an increase in the Niño 3 or E index, or Niño 4 or C index. But this period of the data is not believable. And so you can never tell whether ENSO has affected, global warming has affected ENSO or not. There is also a bias, Khotan bias, which cast doubt on what we had projected. Basically, the mean state in climate model is cooler than the present day climate in the observation. And what kind of impact is not clear. The other biggest problem is that so far, the Eastern Equatorial Pacific, in terms of the trend, is actually cooler. I mean, we project a lot because the Eastern Equatorial Pacific is warming faster than the Western Equatorial Pacific. Critics would argue that that's not seen in the observation. But the other point of view is, in the observation is one world, one realization of real world. is very much dominated by decadal variability. In our projection, we are able to say something because we are averaging off decadal variability, leaving mostly just the climate change signal. Now, the mean state change in the simulation is quite different, although the wind is similar, but this wind is actually reflecting the northern hemisphere ocean is warming faster. So there are many sort of challenges still. So this field is still very active. And in fact, if you look at the meridional gradient and zonal gradient, this is reanalysis. Many models do actually produce similar mean state change. So short period in one world, if you just look at one model, a short period, you can actually produce the mean state change that is similar to the observation. 3 dots represent one real world. Just 3 different reanalysis products. So the bottom line is it's quite likely that answer variability will change in terms of impact, in terms of sea surface temperature. Even if sea surface temperature variability does not change, the extreme event will increase. So that is what I have for you guys. Thank you so much for having me.